Absolutely. Well, first of all, thanks everyone. It's an absolute pleasure. Just a heads up. So this is I'm on my cell phone because we were having some technical issues with the laptop. I've had some issues where like the Wi-Fi will just disappear on me. So if I disappear after 20 minutes, I'll be back. I might be gone for 30 seconds. Anyway, so what I want to talk today about is CLASP. So it's the client process team that went from 2019 and fairly just wrapped up. Well, now it's actually part of more of the GUX glass type of project. So it stands for coupling of land atmospheric subgrid parameterizations. And let me go ahead and give the start of it. So you go to the next slide, please. Okay, so the background behind this is that, so I'm primarily a land surface modeler. So we come from the perspective of land surface heterogeneity. So if you look at a macro scale grid cell, think about 25 kilometer, 100 kilometers, and you see the amount of heterogeneity over the land surface. You have lakes, you have uplands, lowlands, you can have mountains, you can have plains, urban, non-urban. So there's a lot of heterogeneity contained within your classic macro scale grid cell. And how you represent that actually matters because there can actually be very different energy balances. And so that can think about different surface fluxes, Bowen ratios, etc. On the upper left, what you're seeing there is a representation of what we call a tiling scheme. So effectively, to deal with this problem in land surface models, we subdivide our grid cell into these tiles, effectively fractional coverage. So 20% might be grassland, 20% might be urban area, etc. And then what you're seeing on the right-hand side is what effectively emerges. So each of these tiles, you effectively have a histogram or clusters within that grid cell, and each of those is run fairly independently, fed some meteorology from the atmosphere, and they produce their own effectively surface fluxes in most land surface models. And then what happens is that the fractional coverage is then used to aggregate those surface fluxes into what you're seeing as the black line. And that black line historically is what we then feed as a boundary condition into the atmosphere. That is true for sensible heat flux, latent heat flux, etc. And there's a lot of advances that have been going on in terms of tiling as well that I'm not going to necessarily talk about here. But the idea is that we've been putting a lot of emphasis in the land modeling community over the past few decades on improving the representation of heterogeneity in the subgrid. And then the question that emerges, next slide, is what actually happens with all that information that we're producing in the subgrid land when it actually touches the atmosphere. And long story short, up until CLASP, really it was you compute a spatial mean of all these fluxes, regardless of how much heterogeneity you have, and what that atmosphere sees, what your turbulence closure scheme sees as a boundary condition is effectively just the spatial mean. It doesn't actually see any of that heterogeneity, and so that information is then lost. And so what CLASP, the real emphasis of CLASP was, can we actually tie together CLASP, right, effectively these types of parameterizations together, so this tiling schemes in the land surface with effectively the subgrid atmosphere approaches. And can we use this subgrid information over land to inform, for example, the development of convection, enhancement of convection? So within that context, next slide. Next slide. This one, yeah, it's a CLASP framework. So within this context, CLASP was built around effectively these three tasks, which was, one was to develop the parameterization of, and we'll talk about different parameterizations that emerged from it. And the other one was use large eddy simulations tied with the development of new diagnostics to be able to figure out if we were going in the right direction, and use it as a way, in many ways, as a feedback between all these different ideas to then lead to improved parameterizations. And then at the end of it, to do some AMIC style simulations to see the impact of these parameterizations on the global climate. Next slide. So what I'm going to talk about for about 15 minutes is this CLASP parameterization development implementation, all the different ideas that have emerged within CLASP. And then I'll talk about the LES and some mesoscale simulations And then I'll wrap up with where the future direction, where you think the ideas of CLASP can go, and just some general feedback about the CPT model. Next slide. So the first one I want to talk about is club. So many of you are probably familiar with club. So a turbine closure scheme using CSM2 and EFUSM, among others. So club relies on, effectively think about it as a lot of different service, time varying service boundary conditions. And if you look at those service boundary conditions, how we're historically prescribing them from the land model, they weren't really accounting for that subgrid heterogeneity. And so what CLASP was trying to do in one of these thrusts was to leverage the boundary conditions within club to account for the role of subgrid land heterogeneity in club's modeled atmosphere. Next slide. So how we did this, and what I'm showing here is work by folks at PNNL at NCAR as they implemented this into their respective models. And if you see in the lower left, really the idea is that if you think about the turbulence at the surface, you've got the turbulence that's going to emerge from simply local turbulence, and think about that sub 30 a minute, 5-minute time step. But you also have, when you have this heterogeneity, look at the macro scale, you have this additional amount of variance. It's effectively, you can think about it emerging as perturbation around the spatial mean. So effectively, because each of these tiles is going to have a different sensible heat flux, or a different temperature, or different air temperature, or different air humidity, you effectively have a perturbation around the mean, and then you can use that effectively as to increase the variance that you're actually seeing, that you're prescribing into the model. And so I'm showing there on the right is then how that actually impacts a loft, and this is the paper by Meng Huang in 2022. Next slide. As I'll talk about when I talk about the LES part of CLASP, what we did as well was we run WRF LES, where we actually did this over the SGP site in Oklahoma, and we prescribed homogeneous versus heterogeneous surfaces. And then we effectively looked at how the atmosphere responded with one versus the other. And what you're seeing on the left is effectively a representation of what WRF LES was seeing. And the main story that I'll talk about is the idea of secondary circulations, mesoscale circulations. So when you have effectively the subgrid in the sub 100 kilometers, when you have strong, appreciable thermal gradients, that can lead to secondary circulations, which can have a large impact, at least in the context of the LES that we've seen, on the actual enhancement of convection and cloud development. And that what you're seeing, the heterogeneous versus homogeneous in the WRF LES, that is an expression of that. So we tried this also with this implementation of the CLASP club approach, and we did not see nearly as much response. And the short story why is because we really could not get those secondary circulations represented when we simply prescribe boundary conditions or tweak the boundary conditions of club. Next slide. So the next iteration that we did on this, and this is work led by Tyler Waterman, who's a PhD student that works with me at Duke, is we went for something we call a 2-column club. So the idea is, if you think about these secondary circulations as emerging over a large hot patch and a large cold patch, and effectively what emerges is effectively that circulation that is going to effectively bring moisture from the cool patch over to the warm patch, and that warm patch with a higher sensible heat flux is able to push it higher. And that actually then leads to an enhancement of cloud development. And we saw that in LES, and what this paper that Tyler developed is able to actually implement this. So simply with 2 columns, you're able to get this pretty nonlinear effect popping up in your subgrid atmosphere to account for what you're seeing on the surface. Next slide. So in parallel to these club efforts, we also had a focus on EDMF. So this is the CLASP EDMF parameterization. And so EDMF combines an eddy diffusivity with a mass flux term. So think about plumes to model both turbulence and updrafts and downdrafts. So EDMF used an AM4 in GEOS and GMAO, and now in CSM2 at NCAR and in Club MF. So because land heterogeneity is known to produce these secondary circulations, so GFDL and GMAO are focused on their efforts on the updrafts within EDMF. So a little bit different than the club approach. The club approach was trying to focus on the boundary conditions, on the surface boundary conditions to affect effectively the turbulence, that eddy diffusivity. And what the EDMF approach at GFDL and GMAO was really, let's play around with the plumes. And let's see if we can actually have the surface heterogeneity inform those plumes. Next slide. So what I'm showing here is the work that emerged at GFDL, led by Khalid Ghanam. So this was a single plume approach, and effectively what they implemented is accounting for the subgrid heterogeneity over land, these tiles. They used that to more formalize and accounting for the heterogeneity, the updraft area fraction, instead of being fixed, actually use the statistics of the surface boundaries. You have a change in updraft vertical velocity that's accounting for also those surface properties. And what I'm showing there on the bottom then is a global climatology difference. So this is CLASP versus the baseline. So you see the changes in sensible heat flux and you see changes in precipitation. You can see over land primarily, and then there are effects over ocean, but it's unclear if that's just noise or not. Next slide. So the other one is at GMAO, the focus was more on we're going to call a multi-plume approach. So instead of at GFDL, the focus was on a single plume and how do you actually inform that plume with the surface information. At GMAO, the idea is with the multi-plume, if you have all these different patches, so you have warm patches, cold patches, if you look right above, you figure out the patches that are buoyant, right? And if you have a buoyant patch, then that's where you're going to launch your plumes. And you can have the power of effectively, or how powerful those plumes are, being informed by the characteristics at that time over that tile. And I'm showing there on the right then is the 1 tile versus 10 tiles, the subgrid tiles, and how it actually then impacts the PBL. And this is a paper that is currently under review. Next slide. And so then to bring it, in many ways, bring a lot of these ideas together, one thing that the folks at NCAR are exploring after doing the club surface boundary conditions, and as they've moved towards the club MF, which emerged also from a CPT, is to look at this multi-plume approach. So what happens if we have all these, instead of a homogeneous case, which is what the club MF is doing originally, what happens if you actually leverage all these different tiles that exist and you launch these plumes accounting for that information? So similar to what GMAO is doing. And that work is ongoing, but it is exciting in the sense that we're getting closer and closer to this idea of these updrafts that are going to have larger strength and then can be informed as we're from the adjacent tiles, as we see, and then in the secondary circulations from LES. Next tile. Next slide. Okay, so that is the parameterization part. And then what I want to talk about a little further is about the large eddy simulations and the diagnostics, which were also a critical part of CLASP. And as I'll show, the LES really informed a lot of this parameterization effort. Next slide. Next slide. And we can, just go straight to the next one as well. Okay. So one of the efforts that we've been looking at is how do you leverage land atmosphere coupling metrics? So we call them local metrics. And so the idea is, so we implement all these parameterizations for this coupling of subgrid, land and atmosphere. And what is the actual response? So how do things actually change? So this is work led by Zunyan. So he effectively implemented a lot of these local metrics as a way to evaluate that. And so what I'm showing here is examples of mixing diagrams that are really telling us how things evolve over the day and how dry soils and wet soils where is that effectively energy going, and how the class parameterization is changing that. Next slide. Then another thing that emerged from this is a lot of the metrics that we use within our coupled models, and we think about land-atmosphere interactions, it's mostly daily data at which those metrics are computed. And one of the things that emerged from this is if you really want to think about this subgrid coupling, which is really a diurnal cycle, how circulations develop as a product of these thermal gradients, it's very much an hourly type of process. And it's something that it's really hard to evaluate and think about in the context of daily or monthly. And so one of the things that emerged from that is a paper that just came out in GMD by Kirsten, which is emphasizing the need for climate models to be able to produce more sub-daily information so we can actually diagnose this more appropriately. Next slide. Some other work that we did is, so we did some mesoscale modeling. So in the context of irrigation, the folks at NASA were looking at what is the effect of subgrid irrigation on that macroscale response. And so what we're showing here are effectively also those mixing diagrams. And what they did is they have some observations of what the mixing diagrams look like. And they also effectively look at no irrigation versus different types of irrigation data sets. And they're able to show the response that you're seeing in terms of the atmosphere from including this irrigation. Next slide. So as I was mentioning, one of the key things that happened within LES is within CLASP was the large NA simulations. And so this was, the emphasis of this was try to understand the role of multi-scale land surface heterogeneity in cloud development. So what we did here is we forced LES using 100-meter spatial resolution land surface fields run from a high-resolution land surface model over the Southern Great Plains site in Oklahoma. And here I'm showing the example for the 24th of September. I think there's a typo there in the text. But on the right, what I'm effectively showing is we play around with a different amount of heterogeneity on the surface, and while ensuring that the spatial mean is the same. So the amount of effectively energy going into the atmosphere over the entire 100-kilometer grid is still the same. And then we see the response of the atmosphere in the shallow convection day. So you got homogeneous, you have R, which stands for you only have rivers of heterogeneity. Then R plus S is now you have soil of heterogeneity, so you see that in the sensible heat flux. Then R plus S plus LC is now adding land cover heterogeneity. M is only meteorological heterogeneity. So what that actually is there was a scattered thunderstorm the day before that put an imprint of soil moisture into the area. And that then led to the next day of having this blob of cold versus the rest of it being hot. And the heterogeneous, the HTG is the fully heterogeneous. And what I want to focus on is the lower one. So you're seeing liquid water path and TKE. And the TKE especially, if you see the evolution of those different simulations, the moment that you add in those large thermal gradients that you get from the meteorological heterogeneity from the antecedent conditions, you start to get a mesoscale response in that. In the TKE, it's not really the turbulent kinetic energy, it's actually a mesoscale signature, but it leads to a pronounced increase in kinetic energy at those larger wavelengths. And then that leads to actually an enhanced cloud production. So you see actually a large increase in liquid water path. And so it's this signature, this idea of how these spatially organized thermal gradients, how they can actually play a big role. And this is not new, and the class did not discover this. This is something that has been known from the literature quite some time, but we were able to focus it on specifically the emphasis within CLASP. Next slide. One of the follow-ons to that work was expanding this LES to 92 different shallow convection days. I'm not going to go into too many details here, but if you look on the right, each of those points is a day, right? So those 92 days. And what we're trying to figure out is there a connection between the mean spatial sensible heat flux to the circulation strength? So effectively, we know that there is a circulation that emerges in the heterogeneous versus the homogeneous. How predictive is that? can the mean spatial mean of sensible heat flux predict that? And the answer is no. The sensible heat flux over the 92 days cannot predict reasonably well if there's going to be a circulation from homogeneous compared to heterogeneous. However, the spatial variance can, or the spatial standard deviation. And so what that tells us is that you cannot include this effectively effect in the atmosphere simply by prescribing a spatial mean of sensible heat flux. You need to account for something like spatial variance or correlation length or both to be able to include that in your parameterization and get an effect from the atmosphere. Next slide. Just briefly, one of the things that we're also doing is taking diagnostics and apply it to the LES. So this is efforts led by Paul Dermeyer, and really just taking this LES and trying to take your more classic metrics and see how they actually emerge and how they actually vary as a way to validate and also try to understand what the LES is showing versus what our single column models are showing. Next slide. Another way that we think about evaluating this is looking at the club PDFs. So the PDFs that emerge at different levels in your single column model, and then comparing it to the PDFs that we get from the large eddy simulations. So we have in the uppercase a more heterogeneous surface, in the lowercase a less heterogeneous surface. And long story short, especially in the heterogeneous surfaces, what club is representing in terms of that PDF, the relationship or the histogram between your temperature and your moisture is very different than what club is getting, even with this CLASP parameterization at the boundary. And so it brings to light this idea that these secondary circulations are something that we can't just capture immediately as a boundary condition. And we need to think about more like the idea of the two-column model. Next slide. One of the additional efforts that we've been thinking about is how well do our land models actually capture the observed space-time patterns of land surface temperature or sensible heat flux, latent heat flux, etc. And this is related a lot to the large eddy simulations, where if we want to make sure that it's actually going to capture these mesoscale circulations and we can actually parameterize them, our land model better be representing the observed space-time patterns or doing a relatively good job of the space-time patterns of the fluxes. And so I'm showing here is space-time covariance and a way to actually parameterize that. Next slide. And then the last one I want to show here before I then talk about where the ideas of CLASP are going is what we're doing also is evaluating. So we're taking some observations. So this is from satellite from GOES of what the space-time structure of the land surface temperature looks like over multiple summers, and then using that to evaluate what the space-time structure of our land models look like. Long story short is that we still have a lot of work to do to actually represent the space-time structure. So if we want to get these secondary circulations represented within our models, and this is even the case, this is for climate model, but this is also the case for short-term weather prediction. If we want to get these mesoscale circulations represented appropriately, there still is work to be done in terms of making sure that our land models are actually getting that space-time structure of the land represented well. Next slide. So where do we imagine or envision or want future CLASP efforts to go? And so one of the things that I mentioned at the beginning is that, so CLASP started as a CPT. Now it's become a project within the GLASP panel and GWEX. And so it's continuing beyond its original CPT. But one of the things that we're interested in is combining this two-column model approach that Tyler developed with the EDMF multi-plume approach. And you can think about how you parameterize these plumes, these interactions between these plumes in the EDMF as a way to capture these secondary circulations. And there seems to be promise there as a way to move forward. And so that is something that, that we want to explore. Next. So the other one is, how should CLASP interact with global storm resolving models? So we've got the 4 kilometer, 3 kilometer globally, and how can we learn from this? And so obviously, moving completely away from 100-kilometer grid cells, 25-kilometer grid cells, there still is a large need for those types of models. But at the same time, though, there's a lot of knowledge that we can gain from these GSRM models. And so how do we actually leverage that information to inform further parameterization efforts that class type efforts would have? To give an example of this, we've done some WRF over the US at 3 kilometers and homogeneous versus heterogeneous, and we're now starting to use that as a way to go back to the drawing board a little bit to reevaluate these class parameterizations. So there seems to be a lot of potential along that way. Next slide. So one other thing that has emerged from this, so CLASP can be thought of as a macro scale problem, but can also be thought of as when you go down to the 4-kilometer model. So even in the GSRM models, there's still going to be subgrid heterogeneity within your 4-kilometer grid cell. There, it's not going to be so much a mesoscale circulation problem, but you do get into these microscale circulations. So you're going to have still thermal gradients between your forest and your grassland, or forest and lake. And those microscale circulations can really wreak havoc on a lot of the assumptions that we have in Monro-Bukov similarity theory. That is a foundation for how we actually parameterize turbulence within our models at the surface, which then triggers and leads to a lot of what we have for sensible heat fluxes and latent heat fluxes. So really the coupling itself is driven a lot by these small heterogeneities of the land surface. And so in the context of sub 4 kilometers, moving forward, what a future additional CLASP effort would look like is really trying to go back and revisit a Monro-Bukov, like many groups are already doing. I mean, but bring that into the Earth system modeling community as a way to revisit really the coupling as to how we actually arrive at our surface fluxes. Next slide. Okay, so just to wrap up, 2 slides of my opinions of what worked and what we think could work better next time. So from our perspective, it connected land and atmospheric experimentalists and modelers in ways that pulled us all out of our silos. So in many ways, the heterogeneity over land, heterogeneity of atmosphere, different communities have been thinking about them for quite some time, but actually thinking about them together is something that CLASP allowed to do. And in many ways, that was a huge benefit that emerged from that. It jump-started many careers, so PhD students, postdocs, and other early career scientists. This cross-center agency funding approach enabled concrete interactions that are discussed. We think about, well, let's work on this, let's work on that, and we think about panel meetings. But it rarely happens until you actually have some real concrete resources behind it. And so that sense, the CPT approach is able to help quite a bit. Project-wide webinars every 3 to 6 months enabled checkpoints that really helped us to keep it moving along. Especially as I'll talk about in a second with the amount of drag that was produced by COVID hitting at the beginning of this. And then the working groups that we set up along the way around the main themes of the CPT were crucial to keep the momentum going. So we had these 3 working groups that changed over time, and those met on a bi-weekly basis, some of them, and that really helped keep things moving. So what didn't work? I summarize it here in 2, but I can go into more details. So starting right, and this is probably true for all the CPTs, but right when COVID hit, created this immediate incredible drag on getting things up and running, especially that first year. And it felt like paddling upstream for the first year and a half. And the thing that I'll say is that one of the challenges of it as well is there's a need for a more formal, we're going to call overarching cross-agency supervisory board to help ensure more success. So to put some emphasis or some more explanation behind this, effectively each unit or center PI is funded by a different agency. And the initial thrust of the CPT is everyone is coming together, all these agencies coming together to fund this one big project. And what it really would have helped along the way is really to have effectively a board or a supervisory board across maybe all program managers that we talk to on a regular basis as a group to really emphasize the cross-agency perspective of that. And with that, thank you everyone for your attention, and I'm happy to take any questions.
And thank you for a very very nice presentation. I'm just wondering, do you think like the simple parameterization, just embed the entire, the land surface and boundary layer with multiple grid, it can be, eventually larger simulation resolution, just embed every column with such a sort of simple parameterization of the boundary layer and surface interaction, similar to that proposed by them. It seems like actually we should even, you can get the flux corrector, but we want, let's say, have a precipitation down to a particular grid. We really want to know where the water goes. That's highly important to the impact. So with all those information, you have some tires, you still cannot map that into a particular river. How, the river, say, overflow or something flood, how can you really, get to that detailed surface impact? Yeah, basically that's something.
Yeah, I mean,
Well,
what I'll say briefly is, yeah, I mean, the idea of a super parameterization and embedding it, those ideas, I think it's great. I mean, it just comes to a computation type of question, right? So how much do you want to simplify this? And it's how much do you want to be able to run very fast ensembles and multiple ensembles of this versus getting very concrete, high resolution realism. And it's a trade-off. So, I mean, I agree with you. That would be good.
I feel the reason super parameterization, let's say, that's been proposed many years ago, but the reason, let's say, if it's not very successful, it's not because of the computational, it's not affordable. It's more like the quality of the simulation. We haven't seen big breakthrough, like,
Yeah.
But with this land heterogeneity, the coupling, I think we might potentially really see some breakthrough.
Yeah, no,
Anyway,
I have we can chat later, Ming, but we've done these mesoscale simulations, 3 kilometer over CONUS, where we did homogeneous versus heterogeneous, and you can see, and we actually look at like predictability, and you can see an increase in predictability of in the heterogeneous, and so there is, like, when you think about that subgrid problem, there is potential there in terms of like those thermal gradients and the impact circulations, but yeah, I mean I agree with you that it might be the approach of how super parameterizations could be able to actually help. Yep.
Thank you.
Yep.
Right. Other questions?
Yeah, I have a question. Sorry, didn't find the raise hand button. So hi Nate, thank you for the very informative presentation of the project. So I wonder, it's a great idea about the 2-column implementation in CLASP. I wonder if that has only been tested in the single column model, or is I wonder whether that is still scale dependent, and also definitely depend on which kind of heterogeneity you have in the land surface. I wonder, could you comment on that? Thank you.
Yeah, so one of the things that matters a lot in that parameterization is the correlation length. So the spatial structure of the land. So if you have spatially organized thermal information, thermal gradients, that is going to play a much bigger role than if it's just spatial noise. And so in the parameterization, when we actually parameterize the circulation flow velocity, in that parameterization is the correlation length of the structure is in there. So if you have spatial noise, there will not be a circulation. If you have structure, it's more likely to have a circulation. So the scale dependency is going to be in there in that context. In terms of implementation in a global model, currently there's potential doing it within CSM2. With their multi-plume approach, the idea is how do you actually, with the EDMF, how do you actually then can take this information and use it to actually inform it? But specific plans to implement a 2-column model within a global model, it's not there. And it's related to the super parameterization type of question. mean, it's not a super parameterization, but it still is, you're doubling the atmosphere by doing this. And so there has to be an effort to actually put it in there, because it's not trivial just to copy the atmosphere twice. And we've, like, this paper that's currently in review, I mean, it shows that this has the potential to do this, but then we actually have to take it to the next step. And so, yeah, I mean, additional years of CLASP probably would have pushed that forward, but then the project came to an end, the formal project.
Great, thank you.
Yep.
All right, Juliana.
Hi. This is more out of curiosity because it's related to the world I come from. Do you guys have any explicit cross collaboration with the people looking at similar heterogeneity, heterogeneity over the ocean?
The short answer is no. However, a lot of the literature of that community has definitely played a big role when we think about the secondary circulations. So we've not formally done it. I mean, one thing that I will mention, and I'll bring this in terms of future directions, a CPT that looked at the coastlines of land, atmosphere, ocean interactions is something that is very interesting in the concept of circulations, right? So that is the clear, nice place of thermal gradients, right? And so that's a place where you could bring together these communities in a much more succinct way.
Thank you.
Yep.
I appreciate that context. If I could ask, I mean, I have like 4 questions jotted down. I suppose I can always follow up offline, but the question I wanted to ask was kind of more of a practical one, and one that we've actually thought about on the panel a little bit. But you mentioned that one of the things that kind of fell out of CLASP is this paper that you guys just submitted about asking modelers to produce sub-daily information, and not just for like impacts related work, but model evaluation and fidelity. Could you speak, in, I don't know, a minute or two more to kind of where you think we are and whether this should be kind of a default standard for modeling centers?
For what's being produced?
Yeah, like moving forward, if you were to kind of, I don't know, if there was to be like a standard deck that we as a community should really push for in terms of understanding model processes, what are your kind of thoughts on that?
Yeah, I mean, I'm obviously thinking from the bias of my perspective. So the reality from the CLASP type of efforts, and then this is before even CLASP, when you want to think about diurnal cycle of convection, right, over land. So this is very much the sun comes up, the sun hits the ground, it heats up the ground, it develops the boundary layer, you get convection, and you get the afternoon thunderstorm type of stuff. This is very much a subdiurnal problem. And so if you want to be able to diagnose how that's being represented in the models, if you actually want to get to the actual process, it's just a daily metric is not going to cut it, right? And so just simply from a diurnal cycle convection, which is very much persistent, I mean, an idea for all ocean and land, you have to be able to get to the subdiurnal. One of the things that we're also very interested in as well is we have to diagnose the spatial structure of the land. So one of the things that we saw from that is that we're not actually diagnosing the land in ways that are informative for the spatial structure and space and time of the land. And so the premise coming into CLASP was that our land heterogeneity is a very quote unquote advanced. But one of the things that emerged from CLASP is that we realized that actually our space-time patterns of surface fluxes are actually more rudimentary than we actually would like them to be. And so effectively producing space-time information of the surface at that sub-daily, that is stuff of information that you're going to need to be able to advance this subgrid coupling type of idea.
Okay. Yeah, it's appreciated context. I mean, this is one of the things that I think we actually discussed this a few years ago when I first rotated on the panel, was as far as development diagnostics that were useful for folks that were interested in processes within the models, but not necessarily the modelers themselves. And so that comment kind of got me thinking. But of course, the modelers, you know, when I think we brought this up with Jean-Francois Lamarck, was, you know, I mean, if you ask everyone what diagnostics they want at hourly timescales in these models, like suddenly it becomes petabytes of data. You know, a test run, an intermediate run, CSM 2 point data 5, whatever, is going to be petabytes of data. So anyway,
yeah. I mean, like,
kinda,
there's the wish list and then there's the reality. But that paper that came out, which was a lot of not just the CLASP, but also a lot of some GUX GLASS folks. It really was like yes, we understand that this is expensive, but if we want to actually solve this, we need to do more than just. And that was the story.
Yeah. Great. I'll have to go back and take a look at that then.
Yep.